Welcome to today's problem walkthrough. In this session, we'll tackle LeetCode problem number 1375, titled Bulb Switcher 3. This problem challenges us to simulate and analyze a process involving bulbs and switches. We'll explore different approaches and evaluate their efficiency. Let's dive in. In this problem, you are given n bulbs arranged in a row, numbered sequentially from 1 to n. Initially, all the bulbs are turned off. You then turn on the bulbs one at a time, following the order specified by an array light. At each moment k, the bulb at position light, k, is turned on. The goal is to determine how many moments occur when all the bulbs that are currently turned on are also blue. A bulb turns blue if it is on and all the bulbs to its left are also on. For example, if bulbs 1, 2, and 3 are on, and all these bulbs are blue, this would count as one such moment. The output of the problem is the total number of these blue moments. Let's look at the input and output format next. The input is an array light, where each element represents the position of the bulb that is turned on at a given moment. The output is a single integer representing the total number of moments when all the turned on bulbs are blue. Let's start by looking at the first example. Here, the input array is light equals 2, 1, 3, 5, 4. The output is 3, which means there are 3 moments when all the turned on bulbs are blue. Let's break this down step by step. At moment 0, the bulb at position 2 is turned on. However, bulb 1 is still off, so no bulbs are blue. At moment 1, the bulb at position 1 is turned on. Now, both bulbs 1 and 2 are turned on and blue, so this is our first blue moment. At moment 2, the bulb at position 3 is turned on. At this point, bulbs 1, 2, and 3 are all blue, marking the second blue moment. At moment 3, the bulb at position 5 is turned on, but bulb 4 is still off, so there is no blue moment here. Finally, at moment 4, the bulb at position 4 is turned on, making all bulbs from 1 to 5 blue. This marks the third and final blue moment. So, in total, we have 3 blue moments. Now, let's examine another example to solidify our understanding. Here, the input array is light equals 3, 2, 4, 1, 5, and the output is 2. This means there are 2 blue moments in this scenario. Let's walk through the sequence. At moment 0, the bulb at position 3 is turned on. Since bulbs 1 and 2 are still off, there is no blue moment. At moment 1, the bulb at position 2 is turned on, but bulb 1 is still off, so no blue moment yet. At moment 2, the bulb at position 4 is turned on, but bulb 1 is still off, so no blue moment. At moment 3, the bulb at position 1 is turned on. Now, bulbs 1, 2, 3, and 4 are all blue, marking the first blue moment. Finally, at moment 4, the bulb at position 5 is turned on. At this point, all bulbs from 1 to 5 are blue, marking the second blue moment. Thus, the total count of blue moments is 2. Here's another example to further clarify the problem. Suppose the input array is light equals 4, 1, 2, 3. The output is 1, which means there is only 1 blue moment. Let's break it down step by step. At moment 0, the bulb at position 4 is turned on, but bulbs 1, 2, and 3 are still off, so no blue moment occurs. At moment 1, the bulb at position 1 is turned on, but bulbs 2 and 3 are still off, so no blue moment. At moment 2, the bulb at position 2 is turned on, but bulb 3 is still off, so no blue moment. Finally, at moment 3, the bulb at position 3 is turned on. Now, bulbs 1, 2, 3, and 4 are all blue, marking the only blue moment in this scenario. Therefore, the total number of blue moments is 1. Now, let's consider some edge cases. First, for the minimum input size, if there is only one bulb, such as light equals 1, there will always be exactly 1 blue moment because the single bulb will be blue as soon as it's turned on. Next, for the maximum input size, where n is 100,000, the algorithm must efficiently handle this large input while maintaining the logic for tracking blue moments. Finally, consider a highly non-sequential order, such as light equals 10, 9, 8, 1. In this case, we would need to ensure that the solution can correctly track the maximum bulb index that has been turned on and verify the continuity of all bulbs to the left. These edge cases help ensure that the solution is robust and handles all potential scenarios effectively. To solve the bulb switcher 3 problem, we can consider two main approaches. First, there's the brute force approach, which involves simulating the process step by step. The intuition here is straightforward. For each moment k, when you turn on the bulb specified by light, k, you iterate through all the bulbs from 1 to k to check if they are all turned on and blue. This approach uses an array to track the state of each bulb, and each time a bulb is turned on, you perform a leftward check to confirm that all prior bulbs are in the correct state. However, this method has significant drawbacks. It involves repeatedly iterating through the bulbs for each moment, leading to a time complexity of n squared. While simple to implement, it becomes highly inefficient as the input size grows, making it impractical for large values of n. To address these inefficiencies, we can consider an optimized approach that eliminates redundant checks while still achieving the same results. The optimized approach builds on a key observation: a bulb only turns blue if all the bulbs before it are also lit. Instead of tracking the entire state of the bulbs, we can simplify the problem by focusing on the maximum bulb number lit so far, which we call maxlit. If at any point maxlit matches k plus 1, where k is the current moment, it guarantees that all bulbs up to maxlit are turned on, and the current bulb can safely turn blue. This insight allows us to design an efficient algorithm. We initialize two variables, maxlit to track the highest bulb number lit so far and blue moments to count the moments when bulbs turn blue. As we iterate through the array, we update maxlit to the maximum of its current value and the bulb number at light, k. If maxlit equals k plus 1, it means all the bulbs up to that point are lit, so we increment blue moments. Once we've processed all the bulbs, we return the value of blue moments. This approach is both time efficient, with a complexity of n, and space efficient, requiring only 1 additional space. An alternative approach to solving this problem is based on prefix sums. Here, the intuition is to track the cumulative sum of the bulbs lit so far. At any moment, if the sum of the bulbs lit equals the sum of integers from 1 to maxlit, it guarantees that all bulbs up to maxlit are turned on. This method involves calculating the sum of the first maxlit numbers using the formula for the sum of an arithmetic series. While the prefix sum approach has a time complexity of n, and a space complexity of 1, it introduces additional overhead due to the repeated calculation of the sum at each moment. This makes it slightly less straightforward to implement compared to the maxlit approach. Nonetheless, it provides a valid and efficient alternative for solving the problem. After evaluating the different approaches, we chose the optimized strategy of tracking maxlit as our solution. This approach stands out due to its simplicity and efficiency. The key observation that a bulb turns blue when maxlit equals k plus 1 allows us to avoid redundant computations while maintaining an intuitive understanding of the process. Compared to the brute force approach, the optimized method reduces the time complexity from n squared to n, making it scalable for larger inputs. While the prefix sum method also achieves n time complexity, it involves additional mathematical calculations that make the implementation slightly more complex. Ultimately, the maxlit approach strikes the perfect balance between clarity, elegance, and performance, making it the ideal choice for this problem. To solve this problem, we start by understanding the requirements. The input is an array like where each element indicates the position of the bulb turned on at a specific moment. For example, if light I is 3, it means the third bulb is turned on at the I plus 1 th moment. The goal is to count the moments when all bulbs from the first bulb up to the most recently turned on bulb are blue. A bulb is blue only if all bulbs to its left are also turned on. This means there can't be any gaps in the sequence of turned on bulbs. Now, we can break the problem into steps. First, we note that we need to track two key values during the process: the maximum position of bulbs turned on so far, which we'll call max_on, and the total number of bulbs turned on, which we'll call on_count. The key observation is that at any moment, if max_on is equal to on_count, then all bulbs from 1 to max_on are turned on, meaning all are blue, and we can count this as a blue moment. Let's now outline the algorithm to solve the problem. First, we initialize three variables, max_on to keep track of the farthest bulb position that has been turned on_count to keep track of how many bulbs have been turned on so far, and blue_moments to count the moments when all the bulbs are blue. Then, we iterate through the light array. For each bulb position light, I, we increment on_count because a new bulb is turned on. Next, we update max_on to be the maximum of its current value and the position of the newly turned on bulb, light, I. After updating these values, we compare max_on and on_count. If they are equal, it means all the bulbs from 1 to max_on are turned on without any gaps, so we increment blue_moments. Finally, after processing all the bulbs in the array, we return blue_moments as the result. Now let's dive deeper into some key insights about the algorithm. The comparison between max_on and on_count is critical because max_on represents the farthest position of bulbs that have been activated, while on_count ensures there are no missing bulbs in the sequence. For example, if max_on is 5 but on_count is only 4, it means the fifth bulb is on, but not all the preceding bulbs are, so the fifth bulb cannot be blue. This equality check is what guarantees the sequence is complete up to max_on. This approach is also much more efficient than a brute force method of checking the status of all bulbs at every moment. Instead of iterating through the bulbs repeatedly, we reduce the problem to a simple comparison at each step, achieving a linear time complexity of O(n). Additionally, this algorithm handles edge cases like a single bulb, where it's always blue when turned on, or random orders of activation, since the algorithm dynamically tracks the state of the bulbs. To implement this algorithm, we rely on simple scalar variables like max_on and on_count, which require constant space. No additional data structures are needed because we only need to track the maximum bulb position and the count of bulbs turned on, allowing us to process the input array in place. This ensures that the space complexity remains O(1). As for the time complexity, the algorithm involves a single pass through the light array, where each step consists of constant time operations like updating variables and performing a comparison. This results in an overall time complexity of O(n), making the solution both time efficient and space efficient. Let's walk through an example to solidify our understanding. Suppose the input array is light equals 2, 1, 3, 5, 4. We start by initializing max_on equals 0, on_count equals 0, and blue_moments equals 0. At the first moment, bulb 2 is turned on. We increment on_count to 1 and update max_on to 2. Since max_on does not equal on_count, there is no blue moment yet. At the second moment, bulb 1 is turned on. We increment on_count to 2, and max_on remains 2. Now, max_on equals on_count, meaning bulbs 1 and 2 are both on and blue, so we increment blue_moments to 1. At the third moment, bulb 3 is turned on. We increment on_count to 3 and update max_on to 3. Again, max_on equals on_count, so we increment blue_moments to 2. At the fourth moment, bulb 5 is turned on. We increment on_count to 4 and update max_on to 5. Here, max_on does not equal on_count, so there's no blue moment. Finally, at the fifth moment, bulb 4 is turned on. We increment on_count to 5, and max_on remains 5. Now, max_on equals on_count, meaning all bulbs from 1 to 5 are turned on in blue, so we increment blue_moments to 3. After iterating through the entire array, we return blue_moments, which is 3. This means there are 3 moments when all the bulbs that are currently on are blue. This example demonstrates how the algorithm efficiently tracks the state of the bulbs and counts blue moments using the key comparison between max_on and on_count. This solution implements the problem bulb switcher 3 using an efficient approach. Here's a step-by-step breakdown of the code. 1. Initialization. Max_on is used to keep track of the highest indexed bulb that has been turned on so far. This helps us monitor the range of bulbs currently active. Moments is initialized to 0 and counts the moments when all active bulbs, from 1 to the maximum index, are blue. 2. Iteration through the light array. The loop iterates over each bulb in the light array. Here, I represents the 0-based index of the current moment, and bulb represents the bulb being turned on. For each bulb, we update max_on to ensure it always holds the highest bulb index that has been turned on so far. This is done using Python's max function. 3. Condition for all bulbs being blue. At each moment, we check if max_on equals I plus 1. This condition ensures that all bulbs between 1 and max_on are turned on, because I plus 1 represents the count of bulbs turned on so far. If the condition is met, it means all active bulbs are blue, so we increment moments. 4. Return the result. After processing all moments, the variable moments contains the total count of moments when all active bulbs were blue. This value is returned as the result. ### complexity. Time complexity, O(n), where n is the length of the light array. This is because we iterate through the array once. Space complexity, O(1), as we use only two variables, max_on and moments, to store intermediate results. This approach is optimal and ensures the solution runs efficiently even for large input sizes within the constraints of the problem. This is the Java implementation of LeetCode problem number 1375, Bulb Switcher 3. The logic mirrors the Python solution, tracking the maximum bulb index turned on, maxon, and counting moments when all bulbs from 1 to maxon are blue. Key differences include type declarations for variables, use of Java's math.max method, and the structured class definition typical in Java. The solution has a linear time complexity of O(n), where n is the length of the input array. Here, we start with the first example where the input sequence of bulbs being turned on is 2, 1, 3, 5, 4. Initially, we set max_on to 0, which keeps track of the highest bulb index that is turned on, and moments to 0, which counts the moments when all bulbs up to the highest turned on bulb are blue. In the first iteration, bulb 2 is turned on. We update max_on to the maximum of max_on in 2, which becomes 2. Then, we check if max_on equals I plus 1, where I is the current index. Since 2 is not equal to 1, not all bulbs from 1 to 2 are blue, so moments remains 0. In the second iteration, bulb 1 is turned on. Again, max_on remains 2 because the maximum of 2 and 1 is still 2. This time, max_on equals I plus 1, which is 2. This means all bulbs from 1 to 2 are blue, so we increment moments to 1. In the third iteration, bulb 3 is turned on. We update max_on to the maximum of 2 and 3, which becomes 3. Since max_on equals I plus 1, which is 3, all bulbs from 1 to 3 are now blue, so we increment moments to 2. Next, in the fourth iteration, bulb 5 is turned on. Max_on becomes 5 as it is the maximum of 3 and 5. However, max_on does not equal I plus 1, which is 4, meaning not all bulbs from 1 to 5 are blue. Therefore, moments remains 2. Finally, in the fifth iteration, bulb 4 is turned on. Max_on stays 5, and this time it equals I plus 1, which is 5, indicating that all bulbs from 1 to 5 are blue. We increment moments to 3. The final result is 3 moments when all bulbs up to the highest turned on bulb are blue. In the second example, we are given the input 3, 2, 4, 1, 5. Once again, we initialize max_on to 0 and moments to 0. In the first iteration, bulb 3 is turned on. We update max_on to 3, which is the maximum of 0 and 3. However, max_on does not equal I plus 1, which is 1, so moments remains 0. In the second iteration, bulb 2 is turned on. Max_on remains 3, as it is the maximum of 3 and 2. Again, max_on does not equal I plus 1, which is 2, so moments stays 0. Moving to the third iteration, bulb 4 is turned on. Now, max_on is updated to 4, the maximum of 3 and 4. But max_on still does not equal I plus 1, which is 3, so moments remains 0. In the fourth iteration, bulb 1 is turned on. While max_on remains 4, we see that it finally equals I plus 1, which is 4. This means all bulbs from 1 to 4 are blue, and we increment moments to 1. Then, in the fifth and final iteration, bulb 5 is turned on. Here, max_on becomes 5, and it now equals I plus 1, which is also 5. This indicates that all bulbs from 1 to 5 are blue. We increment moments to 2. The final output for this example is 2 moments where all bulbs up to the highest turned on bulb are blue. Now, for the third example, the input is 1, 2, 3, 4, 5, which represents bulbs being turned on in perfect sequential order. Starting with max_on at 0 and moments at 0, we turn on bulb 1 in the first iteration. Max_on becomes 1, and it equals I+1, which is 1. Since all bulbs up to this point are blue, we increment moments to 1. In the second iteration, bulb 2 is turned on. Max_on updates to 2, and it equals I+1, which is 2. This means all bulbs up to 2 are blue, so we increment moments to 2. In the third iteration, bulb 3 is turned on. Max_on becomes 3, and it matches I+1, which is 3. All bulbs up to 3 are blue, so moments increases to 3. In the fourth iteration, bulb 4 is turned on. Max_on updates to 4, and it equals I+1, which is 4. This indicates that all bulbs up to 4 are blue, so we increment moments to 4. Finally, in the fifth iteration, bulb 5 is turned on. Max_on becomes 5, and it matches I+1, which is 5. All bulbs from 1 to 5 are now blue, so we increment moments to 5. Since the bulbs were turned on in perfect order, every moment corresponds to all bulbs being blue. The final output for this example is 5 moments. The time complexity of the given solution is determined by how efficiently we process the bulbs in the input list light. Here, we iterate through each bulb exactly once using a single loop. Within each iteration, we perform a few constant-time operations, updating the max_on variable to track the highest bulb index turned on so far, checking whether this maximum matches the count of bulbs turned on using the condition if max_on equals I+1, and incrementing the moments variable when this condition is true. Since all these operations are O(1), and the loop runs n times for n bulbs, the overall time complexity of the solution is O(n). This linear time complexity ensures that the algorithm scales efficiently with the input size. The space complexity of this solution is minimal because it only uses a small, fixed amount of extra memory. Specifically, we use the variable max_on to track the maximum bulb index turned on so far, which requires O(1) space. Similarly, the moments variable, used to count the number of moments when all bulbs are blue, also requires O(1) space. Additionally, temporary variables like the loop index I and the current bulb value bulb are used during iteration, but these two consume only O(1) space. No additional data structures are introduced, and the input list light is accessed read-only. Thus, regardless of the input size, the space complexity of the solution remains O(1), making it highly memory efficient. When comparing the optimized solution to a naive approach, the differences in efficiency become clear. A naive solution might involve checking the state of all bulbs up to the maximum index each time a new bulb is turned on. This would require either scanning the array or maintaining a separate array to track bulb states, resulting in an O(n)² time complexity due to repeated scans for each bulb. Additionally, the extra array would lead to an O(n) space complexity. In contrast, the optimized solution eliminates the need for such checks or additional data structures. By relying on the condition that the maximum bulb index equals the count of bulbs turned on so far, we ensure that all bulbs up to the maximum are blue without further verification. This approach achieves a time complexity of O(n) and a space complexity of O(1), significantly improving both time and memory efficiency. The time complexity of O(n) holds consistently across the best, average, and worst cases because the algorithm processes each bulb in the input list exactly once, performing a fixed number of O(1) operations per bulb. This ensures linear behavior regardless of the input configuration. To mathematically verify this, consider that for an input list of size n, the algorithm iterates through the list once. During each iteration, it performs a constant number of operations, leading to a total of O(1)*n operations. This results in T(n) equals O(n), confirming the linear growth in time complexity. The uniformity of this behavior guarantees that the solution remains efficient even as the input size increases. One of the most common mistakes in this problem is misunderstanding what blue means. Many candidates assume that it only refers to the current bulb being turned on, but the correct interpretation is that all bulbs up to the current position must be lit. This misunderstanding often leads to logic errors when checking conditions. To address this, it's critical to carefully read the problem statement and clarify any ambiguities, especially during interviews. Another frequent pitfall is using a brute force simulation approach. While it might seem straightforward to repeatedly check all bulbs, this can result in n² complexity, which is far too slow for large inputs. Instead, look for patterns or properties, such as tracking the maximum index of bulbs turned on so far, to optimize your solution. Finally, don't overlook edge cases. For instance, what happens if there's only one bulb, or if bulbs are turned on in reverse order, like 3, 2, 1? Testing your solution against small and edge case examples can help catch these issues early on. Another common error is off-by-one mistakes in index calculations. This is especially tricky in problems that use one-based indexing, as it can lead to subtle bugs. To prevent this, use clear variable names and double-check your indexing logic. Additionally, some candidates ignore constraints like the maximum number of bulbs, which might be as large as 10 to the power of 4. Overlooking these constraints can result in solutions that time out on larger test cases. Always analyze the problem's constraints carefully and ensure your solution scales well, even for the worst-case input size. This is a critical aspect of building efficient and reliable algorithms. To excel in interviews, it's important to focus on patterns. Many array and sequence problems can be simplified by spotting mathematical or logical patterns. In this problem, for example, tracking the maximum bulb index turned on and comparing it to the count of bulbs turned on is a key insight. Interviewers also value candidates who can optimize their solutions early. While starting with a brute force approach can help demonstrate your understanding, it's crucial to quickly identify and implement optimizations for problems with high time complexity. Communicating your assumptions and how you handle edge cases is another important skill. It shows that you're thorough and thinking critically about the problem. Lastly, adopt an iterative problem-solving approach. Start with a simple solution, even if it's not optimal, and refine it step by step. This structured thinking process is often more important than arriving at the perfect solution immediately. If you're looking to practice related problems, here are some excellent options. First, LeetCode 1365, how many numbers are smaller than the current number, focuses on counting and comparisons within an array. Next, LeetCode 769, max chunks to make sorted, involves dividing an array into chunks based on conditions, which is conceptually similar to this problem. Another interesting challenge is LeetCode 798, smallest rotation with highest score, which deals with optimizing rotations for a scoring condition. Finally, LeetCode 1007, minimum domino rotations for equal row, is a problem that tests your ability to minimize operations while meeting specific conditions. These problems can help you build a deeper understanding of array manipulation and optimization techniques. There are several alternative approaches to solving this problem. One effective method is optimized simulation with maximum tracking. Instead of repeatedly checking all bulbs, you can track the maximum index of bulbs turned on so far. If this maximum matches the number of bulbs turned on, you know all bulbs up to that point are blue. This approach achieves O(n) time complexity with O(1) space, making it highly efficient, though it requires careful implementation. Another option is to use advanced data structures like a Fenwick tree or segment tree. These structures allow you to maintain the state of the bulbs efficiently and can handle additional queries if needed. However, they come with added implementation complexity and operate at O(n log n) time. Finally, a mathematical approach might be possible, where you derive an invariant or formula to track the required conditions without explicit simulation. While this method can lead to elegant solutions, it requires deeper insight into the problem's structure and may not always be straightforward to discover. Great work making it to the end. To summarize, we reviewed the problem, explored an approach, and discussed its strengths and trade-offs. Remember, practice is key to mastering coding challenges. Thanks for watching, and don't forget to subscribe for more problem walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!